When we imagine the solar system, we tend to have this concept of a flat disk with lots of rings indicating the orbital motion of the planets. Given that we've learnt this since we were little, we kind of take it for granted that all the planets are on the same orbital plane. Not only that, but they all orbit the Sun in the same direction. But have you considered why? Is it a massive coincidence? Or did something happen to make it this way? And if there was a process, do we have evidence of it elsewhere? As you can probably guess, it was not a massive coincidence. Because not only do we observe planets orbiting the Sun along a plane, regular moons do too. All the gas giants have regular moons that also orbit along the planet's plane, and in the same direction too. Saturn's rings orbit Saturn along the same plane as Saturn's regular moons, in beautiful clockwork fashion. So we can see that there are plenty of examples, but how and why did this all happen? Let's go back billions of years ago to before the solar system was formed. Deep in the heart of an H2 nebula, or a stellar nursery, gas and dust were suspended in place, each particle resisting the other's gravitational pull with an internal repelling pressure. Until one day, an outside push of energy, like a supernova shockwave, jolted the gas and dust inside the nebula, disrupting the inward pressure, causing the particles to collide and clump together. Soon these clumps would attach to other clumps, their mass and gravity increasing with every particle becoming attached. Within a few thousand years, impacts from the infalling material began to get more energetic, causing the object in the center to heat up. More material from the nebula cloud was sucked into the object as its mass and gravity increased, forming what is known as a protostar, or a very young star that hasn't started nuclear fusion in its core yet. At first, the infalling material around the protostar would have been pulled in from all directions, causing a very chaotic environment around the protostar. Collisions between the particles would have happened on a regular basis, and through doing so, their angular momentum would have been cancelled out. However, these infalling particles would not have approached uniformly, as the collapsing nebula cloud has a total angular momentum. So what ends up happening is that while particles approached from all directions, most of their momentum would have been cancelled out by particles going in other directions, until all you are left with is the direction most particles were going. The best visualization I can give you to help you wrap your head around this concept is this. This is a great video from Dan Burns, who uses a sheet of lycra to represent space-time. The ball in the middle, with its large mass, is warping space-time and creating gravity, which is just like what gravity does in three-dimensional space in the universe. Dan throws balls in both directions around the central object, and the balls orbit until they collide with another ball going the opposite direction, cancelling their momentum out. And what you are left with are just the balls that didn't collide and are all going in the same direction. Now, friction from the lycra wouldn't happen in space, so you can imagine particles continuing to orbit, unlike the balls that slow down eventually on the lycra. Also, this is kind of a two-dimensional representation of what happens on a three-dimensional plane in a four-dimensional universe, so you'll need to imagine these particles going along another axis too. Instead of just the two directions these particles approach from, around a protostar, they will be approaching from all directions, colliding and cancelling each other out until only the predominant direction remains, creating a protoplanetary disk. As material falls into the protostar, the angle of the impacts cause the protostar to begin to rotate in the same direction the disk is spinning. As less matter falls towards the protostar and instead begins to stay in orbit around it, material begins to clump again. If enough material clumps into one, you may end up with another star, making it a binary or even a multi-star system. Otherwise, these clumps will eventually coalesce into planets. Around these planets, a similar disk to protoplanetary disks form, again causing the planet to rotate in the same direction as the disk, and the material in the disk eventually forming moons. This clumping of material can be observed even today, with the planet that has a mighty disk of its own, Saturn. Cassini, during its mission, was able to spot tiny moonlets forming within Saturn's rings as material clumps together from various gravitational interactions. Some of these moonlets fell apart soon after, as I'm sure also happened in our early solar system. But some lasted until the end of Cassini's mission, and perhaps they will eventually form very tiny moons one day, like some of the other shepherd moons that have carved paths in the rings themselves. Now, the orbital plane of the solar system isn't perfectly flat. Some planets have variations of a few degrees, but it definitely is a pattern. It's almost beautiful how in nature you can have something so chaotic that will eventually form something rather calm and orderly. As material in the solar system like asteroids and comets continue to find homes on the planets by impacting them, less and less collisions will happen. We can already see a vast reduction in the amount of collisions that have taken place by measuring the age of craters on exposed celestial objects like the moon and others. From these clues, we can see that all the planets were heavily bombarded from asteroids and planetesimals during this chaotic beginning, the amount of collisions gradually reducing as more material got in order, until what we see is the solar system we have today. This is a type of natural phenomena which falls under something called emergent structures through self-organization. Other self-organizing emergent structures are strongly comparable to this process. For instance, the development of hurricanes. Emergent structures are basically where randomness can give rise to complex and deeply attractive orderly structures. We see self-organizing take place in space with orbital planes in planetary systems, solar systems, and even in galaxies. As a side note, we also see it in star and planet formation, and to a large extent, the Big Bang. Given all this evidence, we have to assume that similar processes formed other star systems, and we have just about been able to observe massive planets orbiting other stars along similar planes too. When I was much younger, I had this dream of going to Jupiter and throwing a match in, setting its hydrogen ablaze, and having a second star in the solar system. There were obviously some problems in the way of executing my plan, not limited to the fact that there is no oxygen to ignite the hydrogen on Jupiter. But that doesn't stop the question of whether Jupiter could have been a star, had things gone a little differently. Is Jupiter a failed star? And the answer is yes and no. No, in that Jupiter is not something called a brown dwarf, which, by its very definition, is a failed star. Brown dwarfs are much more massive and hotter than Jupiter. They generally form independently of other stars, in a molecular cloud where other stars are formed. This video is a computer simulation of a molecular cloud collapsing and forming stars. As you can see, some objects are flung away from the cloud before they've had time to acquire enough mass to become real stars. These are likely to become brown dwarfs. On the other hand, you have objects that continue to pull in more mass from the cloud. These will become main sequence stars. Zooming in on a star forming, you can see that a disk of gas and dust from the molecular cloud has formed around it. This is called a protoplanetary disk, and this is where planets eventually form. You can see the making of planets start to blob together over time, and it's from this disk that we believe Jupiter came from, just like the other planets in our solar system. But aren't there loads of star systems out there with more than one star? That is true, but multiple star systems may have formed when two or more stars met up in the stellar nursery, and stay together, like these ones. An object like our Sun was too greedy for Jupiter during its development and ate most of the mass from the cloud itself. Just to give you a comparison, the Sun contains 99.8% of the mass of the solar system. Jupiter only contains 0.1%. Jupiter's problem was that it formed in the Sun's own disk, and the disk was exhausted before it had a chance to get massive enough itself. So, going back to the original question, yes, Jupiter is a failed star in that it failed to become a star, but that also happened with all the other planets. Ever wondered where the boundary of our solar system lies? Is it up until the orbit of Pluto? The Kuiper belt? Beyond? You may have heard that the Voyager spacecrafts have already left the solar system, their current position putting them well beyond the orbit of Pluto. But in reality, to say they have left the solar system is not really true. So how do we define the edge of a solar system? And following on from that, how big can solar systems get? Let's look first of all at where the Voyagers are, and why some say they have left the solar system. Astonishingly, the Voyagers, which launched in 1977, are still operational today, although at reduced capacities. Their power sources are radioisotope thermoelectric generators, which are great at providing power without the need of solar panels. However, with every passing year, the radioactive material degrades, producing less power. They are currently operating with about half the power they had when they started, meaning a few of the instruments have had to be turned off. What they are currently monitoring is the magnetic field environment of deep space and its interactions with the solar wind. Of particular interest to scientists is the boundary where the magnetic field and the solar wind of the Sun are overcome by interstellar wind, this boundary known as the heliopause. Scientists think that Voyager 1 crossed this boundary in 2012 and Voyager 2 crossed it in 2018, both being the only spacecraft to make it into interstellar space so far. What they found out on their journey is that this boundary is not a spherical ball around the Sun, but is rather bubbly and asymmetrical. And much like planets facing into the Sun with their magnetic fields trailing behind them because of interactions with the solar wind, the Sun's magnetic field also trails behind against the interstellar wind. As the solar system orbits the center of the Milky Way, it travels at over 800,000 kilometers per hour. As it moves, it passes through what is known as the interstellar medium at relative speeds of 80,000 kilometers an hour. This creates a kind of wind effect on the magnetic field of the Sun, leaving a tail in the interstellar wind's wake. But as fantastic as the Voyager mission is, reaching interstellar space is not the same as reaching the edge of the solar system. The edge of the solar system is defined by gravitational influences, a boundary known as a Hill sphere. Although it should be noted that this is not really a sphere either. I'll come to that in a bit. A Hill sphere is the region around an object where the gravitational pull of that object overcomes the gravitational pull of anything else. For instance, the Moon orbits the Earth because it is within the Earth's Hill sphere. It's close enough that the Earth's gravitational exertion on the Moon dominates the Sun's. Satellites orbiting the Moon are within the Moon's Hill sphere, where the Moon's gravity at that distance has a greater pull than that of the Earth and the Sun. And everything orbiting the Sun is within the Sun's Hill sphere, where the Sun's gravity overcomes that of nearby stars. This is the true boundary of the solar system. Now, looking at our local neighborhood of stars, we find that they are unevenly distributed around us. This means that the Sun's Hill sphere isn't really spherical. Take the Alpha Centauri system for instance. It is roughly 4 light years away from us, yet Alpha Centauri contains 2 Sun-like stars, so its total gravitational influence will be greater than the Sun's, pushing the boundary of that part of the Hill sphere closer to the Sun. On the other hand, looking the opposite direction to Barnard's star, we have a red dwarf star that is 6 light years away and much less massive than our star, so the Sun's gravitational influence would stretch much further in that direction. And even if an object is orbiting within the Sun's Hill sphere near the boundary, its orbit is very precarious. The gravity of the Sun here is incredibly weak. The object's orbit would be very slow, and the slightest perturbation might knock this object out of orbit. That's why astronomers currently think the furthest objects can safely orbit the Sun is up to a maximum distance of 1 light year, even though the Sun's Hill sphere might stretch out for 2 to 3 light years. So, what's out there at that distance? Anything at all? Well, way beyond the Kuiper belt, which is the asteroid belt beyond the orbit of Neptune, up to a distance of about 1 to 3 light years, is a region known as the Oort cloud. We believe the Oort cloud is a sparsely populated region surrounding the Sun, containing billions or even trillions of icy bodies. We believe that's where a small percentage of the long period comets come from. Comets which have orbits of tens to hundreds of thousands of years long. To give you some perspective about the size of this cloud, it will take Voyager 1 300 years just to reach the beginning of the Oort cloud, and potentially 30,000 to 150,000 years to pass through it. Astronomical distances are simply mind-blowing. And remember, at this distance, we are considered to still be within our own solar system. Now imagine how many solar systems there are out there. Which brings me on to the final point of this video. How big can solar systems get? Well, it's something we can't know for sure, although we can have an educated guess about what it would look like. We'll stick strictly to stars for this thought experiment. To include black holes would be to include entire galaxies. The theoretical limit of a star is around 150 solar masses, or 150 times the mass of our Sun, although there are some stars out there that test this theory, like the most massive star that we know of, R136A1, which is apparently 300 solar masses. Now, this star resides in a very densely packed cluster, so although it is massive, its gravity competes with a lot of nearby stars. This reduces the size of its Hill sphere considerably. Let's say a star of this size was somehow ejected from its local cluster, even its local galaxy, and finds itself completely alone in space. With no other gravitational forces for many light years in any direction, the only other competing mass is other galaxies themselves. That means, with nothing competing against it, such a solar system could be hundreds to thousands of light years across, comparable in size to a galaxy, depending on the distances involved. In a universe where only this star and a second smaller object exist, that second object could be billions of light years away and still be in orbit. Because gravity doesn't care how far away the objects are, it will still have an influence on them. In such a universe, the only escape for the second object from the gravitational pull of the larger object would be to have an infinite distance between the two, which isn't possible. So, there we have it. Solar systems are already mind-bogglingly large, and under the right circumstances, they can be far, far larger still. The thought that sticks with me after researching all this is that the universe truly is a fascinating place. Some of you may remember my first video I ever did on my channel, which was how big is our solar system if the sun was the size of a football or a soccer ball. Today I'm going to do that again, but this time I'm going to scale it down a little bit, where the sun is only the size of 1 millimeter, like a grain of sand. We're going to see how big the solar system is in comparison to the sun being that big. So we'll start off first of all with the sun. I'm going to put it just by here. Now the closest planet to our sun is of course Mercury. And if the sun was 1 millimeter in diameter, that would mean Mercury is 4 centimeters away. So I'm going to put it just by there. There's Mercury. So the next closest planet to the Sun is Venus, and it is 8 centimeters away. So there we have Venus. The next one is us on Earth, and that is 10 centimeters away. Then we have Mars, which is 16 centimeters away. The next one we'll mention here is Ceres, the dwarf planet found in the asteroid belt, and that is 30 centimeters away. Okay, the next one is Jupiter, and that is 56 centimeters away. We're getting far away now. Saturn is 1 meter and 3 centimeters away. Coming to the first of the ice giants now, we find Uranus, which is massive, 2 meters and 6 centimeters away. The last real planet in our solar system is Neptune, and that is 3 meters and 24 centimeters away. And then we have Pluto, which is 4 meters and 22 centimeters. And this is the last thing that we'll look at in our solar system. At this point you may be wondering, well, what about the closest star, Alpha Centauri? Well, you're going to have to follow me a little bit, so come on, let's go. I know this wasn't really a straight line, but yes, Alpha Centauri, if the sun was the size just 1 millimeter, Alpha Centauri is 30 kilometers away, and that's our closest star. The solar system is an amazing place, but how much do we actually know about it? Well, in this video, we're going to be having a look at that. And we're going to start off with this, the sun. A nice Adidas F50 ball. Adidas, if you want to give us anything for product placement, you know, it'd be greatly received. But yeah, so this is going to be our sun. It's 11 inches across. And we're going to see how big the solar system is in comparison to our sun. So let's start working, shall we? Let's go towards Mercury. All right, we're about 38 feet away now. That's how far Mercury is in comparison to where the sun is. So let's have a look. Here is Mercury in comparison to the sun. only a tiny blip, really. And obviously, it gets pretty roasted by here. It's pretty close to the sun. It's taking the full blast of the sun's rays. Let's keep going though. Let's go to Venus. All right, so this is how far Venus is from the sun. If you have a look, just behind that car is where we started off. And let's see how big Venus is in comparison to the sun. It's this blip here. Again, pretty small. And again, it's also pretty hot because we're still pretty close. Now the Earth is pretty close to Venus. They say it's its sister planet. And again, it's about the same size as Venus, really, slightly bigger. But this is the perfect place for a planet to be to support life, as far as we know anyway. Obviously, we live here. We're enjoying a nice day, warmed by the sun's rays. So let's keep going. So here we are by Mars now. Now Mars is slightly smaller than the Earth, and it's pretty far away. It's getting a bit colder now. And let's have a look, see how big Mars is in comparison. It's probably this one by here. Roughly. We're getting further and further away now. Pretty far. And these distances are going to keep growing as we go further out. Alright, we're getting pretty far away now. Now this is where the start of the asteroid belt is. An asteroid belt contains millions of asteroids from our solar system. And it's this huge belt, and it begins about here. And it'll go on for about another 100 feet. So, let's keep going. Alright, we're gonna have a little stop here because in the asteroid belt is this planet called Ceres. And it's about 277 feet away from where the sun was. Now, it's a very, very small planet. If I could point it out here, in comparison to the sun, it's probably like this one here. Very, very small indeed. But we call it a planetoid, really, because it's still pretty big. It's round. It's big enough to have a spherical shape. So I thought I'd mention it here as I find it quite an interesting thing. So just to mention, this is the end of the asteroid belt. If you can imagine how far we've walked and how many asteroids there must have been in that section. Literally millions. And we know about millions, and there's probably more still that we don't know about. Pretty dangerous indeed. These asteroids can be very small, anything from a tiny speck of dust to objects kilometers wide. Just so you know. Going through the gate. Okay, so Jupiter is about 5 times as far away from the sun as Earth is. And from this distance, it's getting pretty cold. Surface temperatures on the moons and the planets around here are pretty cold. Now let's have a look, see how big Jupiter is. Jupiter is our biggest planet in the solar system. And still, it's quite small in comparison to the sun. I really love Jupiter though. They call it the solar system's vacuum cleaner. It protects us from all those asteroids and comets which come towards us. Let's keep going. Just headed on to the football pitches now. And this is where Saturn is. And Saturn, apart from Earth, is like... See how big it is? Just imagine it has rings, obviously, compared to the sun. Reasonably big still. Smaller than Jupiter, but still reasonably big. And yeah, we're about 939 feet away from where we started now. Okay, so we've walked a considerable distance now. We're at 1,890 feet. And we've just come up to Uranus, or however you want to pronounce it. And this is it in comparison to the sun, which is quite funny really, because we consider these things to be the gas giants of the solar system. And as you can see, it's not really that giant in comparison to the sun. But still a very interesting planet. It spins on its side rather than that way. Don't know how to explain that.
Sweet.
Let's keep going. We're going to Neptune now. Alright, we've walked quite a ways now. We are 2,963 feet away, which is 30 times further away from the sun than Earth is. And we're at Neptune now, which is, again, pretty similar in size to Uranus. So this is it. And beautiful dark blue color. So we've come this far. We're going to swap now. Swap presenters over. We're going to have Jonathan present for us now.
Well, hello everyone, and welcome to the show. Let's walk and let's see where we're heading next. We are at Kuiper Belt, and it's about starting with 3,000 feet from the sun and goes until 5,000. So let's see how long we're going to walk from 3,000 to 5,000 feet. So we're here. Now this is the place where we find our beautiful, it's not really a planet, but we find Pluto. Now Pluto is about the size compared to the sun. This little thing here, this little piece. This is the biggest object in the Kuiper Belt. Now the Kuiper Belt, I didn't explain it to you before, is mainly a lot of asteroids. Like, it's a belt of asteroids that just goes way around the entire system, and it's made basically out of ice and a few rocks. Now we are about halfway through the Kuiper Belt and we have still to go on. Now back again, but we're still in Kuiper Belt. Now if you think about, we came to a planet called Haumea. Haumea is about 4,300 feet away from the sun, so it's getting pretty freaking cold here. Now if you think about a little piece of dirt here that would be compared to that planet, it would be more likely like this little piece here. Now this stone is so small that you can see it. You barely can see it on the tip of my hand. If you compare it to the sun, it's like a, I don't know, little piece of dirt. Now we're going on for the next planet, which is called Make. It's only 200 feet away from here. So let's go. Oh, sorry, I was bouncing I bounced the sun, you know. Don't worry about it. It won't mess up our solar system. In real, it would. But now we came to a beautiful little dirt called, or planet called Make. It's about 4,500 feet away from the sun. And again, this is a place not for humans. Humans could not live there. Now, if you think about the little dirt I showed to you, the size of Humea, it's about the same. So it's a little piece of dirt. Now let's go to the end of the Kuiper belt. We're coming close to it. It's only about 500 feet from here. So let's go. Now back again. We finally reached the end of the huge Kuiper belt, which is ginormous. If you should think about 3,000 to 5,000 feet from the sun. Now this is a ginormous asteroid belt, and we finally reached the end.
La, we're waiting for our line. We're so obedient. Oh, it's green.
Now back again. Now we finally reached the furthest planet we know of. It's called Eris. It's about 68 times further away than the sun to the Earth. Now, as we know about this planet, it's about twice the size of Make and Humea. So it's not very large.
Top 10 misconceptions about our solar system. Do you think you know what's what about our solar system? My name is HumbleBee and you're watching Astrum. We're going to count down the top 10 misconceptions about our solar system. Let's see if you believed any of these before watching this. 10. The sun is a burning ball of fire. The sun is glowing, not burning like a fire. The sun glows because its temperature is about 5,500 degrees Celsius. This heat is not produced by burning, a chemical reaction, but rather by fusion, a nuclear reaction. This nuclear fusion takes place deep in the sun's core at a temperature of about 15 million degrees. As the heat travels out through the sun's layers, it becomes much cooler, but still very much hot enough to glow in visible light. Now, while 5,500 degrees seems cool compared to 15 million degrees, that's still hot enough to melt most metals. Just to give a comparison, a wood fire burns at about 500 degrees. 9. Pluto is the most distant and last object in the solar system. Pluto resides within a region of icy objects called the Kuiper belt. The Kuiper belt extends from Neptune's orbit outward. Beyond Pluto's orbit is another vast region of icy objects called the Oort cloud, which, like the Kuiper belt, is a home to icy comets. There's even 4 dwarf planets that we know about that are further, and some even bigger than Pluto. There's Haumea, Makemake, Eris, and Sedna. Eris is currently about 3 times as far away from the Sun as Pluto, and Sedna, which has not yet technically been classified as a dwarf planet, although it pretty much is one, can be a massive 937 astronomical units away from the Sun. That, in other words, is 31 times Neptune's distance from the Sun. Some astronomers even believe it is the first known member of the inner Oort cloud. 8. Saturn is the only planet with rings. While many of us were taught in school that Saturn had amazing rings made up of small rocks, ice, and other particles, there are actually several other planets that also have rings around them. In fact, all of the larger planets in the solar system have been found to have rings. This is true of Jupiter, whose rings cannot be seen from our planet, as well as Neptune. Even Uranus has 9 bright rings around it, as well as a few fainter ones, but all of these are difficult to see due to the distance. 7. Comets come from regions outside the solar system. Comets are part of the solar system. Scientists believe they come from one of 2 locations within the solar system, the Kuiper belts and the Oort cloud. The comets that we see often, every 100 years, come from the Kuiper belt, and comets that we see rarely, every few thousand years, come from the Oort cloud. 6. Asteroids in the asteroid belt are very close to each other. Thanks to Star Wars and other Hollywood space movies, we have the impression that asteroids are always bashing into each other and spaceships would have a hard time navigating an asteroid field. Asteroids, though, are not close to each other. The asteroid material is so thinly distributed that numerous unmanned spacecraft have traveled it without incident. On average, they are roughly 1 million miles from each other, and the total mass of the asteroid belt is only just 4% of the mass of the Moon. 5. Mercury is tidally locked to the Sun like the Moon is to the Earth. For many years, it was thought that Mercury was synchronously tidally locked with the Sun, rotating once for each orbit and always keeping the same face directed towards the Sun, in the same way that the same side of the Moon always faces the Earth. Radar observations in 1965 proved that the planet has a 3-to-2 spin orbit resonance, rotating 3 times for every 2 revolutions around the Sun. The original reason astronomers thought it was tidally locked was that whenever Mercury was best placed for observation, it was always nearly at the same point in its 3-to-2 resonance, hence showing the same face. 4. Mercury is the hottest planet in the solar system. While it is sensible to think that Mercury is the hottest planet due to it being the closest planet to the Sun, it's just simply not true. It turns out that Venus is actually a hotter planet than Mercury, even though it is further away. The reason for this is that Mercury doesn't have an atmosphere because it's so close to the Sun, which means that there is nothing to hold the heat in. Venus, on the other hand, has a notoriously thick atmosphere that traps the heat created by the Sun. The max temperature you'll find on Mercury is 426 degrees Celsius, while the average temperature on Venus is 462 Celsius. 3. The Sun only accounts for a small part of what's in the solar system. I'm sure you guessed the Sun is big, but the Sun actually makes up over 99% of all of the mass in our entire solar system. Jupiter and some of the other large planets make up most of the rest, and Earth barely even registers in the equation. We can be glad the Sun is as large as it is, though, as it makes everything in the solar system work, giving us light, heat, and energy, while holding everything together in their orbits using its massive gravity. 2. Comets always have tails. Comets do not always have tails. They develop a fuzzy shell-like cloud called a coma, and 1, 2, or 3 tails when near the Sun. A comet tail and coma are illuminated and may become visible from Earth when a comet passes through the inner solar system. The dust reflecting sunlight directly, and the gas is glowing from ionization. Interestingly, while the solid nucleus of comets is generally less than 50 kilometers across, the coma may be larger than the Sun, and ion tails have been known to extend 3.8 astronomical units, 355 million miles. Also, the tail will always point away from the Sun. Comets have no coma or tail when far away from the Sun. 1. The solar system formed during the Big Bang, along with the rest of the universe. The solar system is a lot younger than the universe. According to scientific research, the current estimate of the age of the universe is 14 billion years. While it is believed that the solar system is only 4.5 billion years, the solar system is said to have formed from the gravitational collapse of a giant molecular cloud, most of which became our Sun, the rest forming everything else found in the solar system.
Thanks for watching. Making this video required some long-term planning and work, which we were only able to do thanks to the consistency and sustainability of your memberships as Astronauts on Patreon. A huge thank you to everyone who has signed up, and if you'd like us to make more videos like this, you can join with the link down below. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.